These two reactions that you're going to learn about in this online lecture are two of the simplest reactions that we have. They're very easy to understand. Hydrogenation is the addition of hydrogen, a hydrogen molecule, across a double bond, and this actually causes reduction of the carbons. Anytime you increase the number of hydrogens on a carbon, you are reducing it. Anytime you increase the number of hydrogens on an oxygen or a nitrogen, you are reducing it. So this is reduction. To add hydrogen across a double bond, you have to have two things. You've got to have hydrogen gas and you've got to have a catalyst. These other things like acetic acid or some other solvent, those things are not the key to it. The key is having hydrogen gas and a metal catalyst. What kind of catalyst do we use? We usually use one of these transition metal catalysts that involve platinum, rhodium, palladium, nickel, and there's a lot of possibilities. Sometimes it's a compound, sometimes it's an organometallic compound. How is it that you recognize the reagent is one that's going to cause hydrogenation? You recognize it because there will be hydrogen gas, and then it will be either the transition metal naked or the transition metal in a more complex compound. And if you see that, then you know you're going to have hydrogenation. Notice when we add hydrogen across this double bond that it is syn addition. They're on the same side. 1,2-dimethylcyclohexene therefore becomes cis 1,2-dimethyl. The mechanism is really rather interesting. What happens is a molecule will come and sit down on the catalyst. Once it sits down on the catalyst, the hydrogen, see this is hydrogen gas molecules, they've already been absorbed onto the catalyst as individual little hydrogen atoms. So what will happen is this will come down and sit down here and just get stuck on the catalyst. So the alkene will get stuck on the catalyst, and notice its double bond attaches it to the catalyst. Then what happens is the hydrogen that is on the catalyst actually will go over and be picked up by the alkene like that, and then another will pick it up, and then what happens is it's free. So and then more hydrogen gets absorbed onto the surface of the catalyst. And this is what causes the syn addition. If you look at how it went and sat down, when it sits down on the double bond, it actually sits down on there, and it does it from one side. However, there is some interesting things that can go on here. If you don't have enough hydrogen to react with that double bond can come off the catalyst without having had reacted with the hydrogen. When it does, oftentimes it can rotate around that double bond before being released. And this is what they call partial hydrogenation, and that's what you hear about that makes the trans fatty acids. And we can go into that later on. Okay, the details of hydrogenation are that you are selective for a double bond, you have syn addition, and steric effects can be really important. What are steric effects? If one side of a double bond is more hindered than another, the side that is hindered by something bulky like these two methyl groups will not be hydrogenated. So when you go to take this molecule, alpha pinene, and you hydrogenate it with palladium, what you find only being made is a hydrogen added from the bottom side of this molecule away from where the methyl groups are on the bridgehead. In epoxidation, we have another very simple mechanism and a very easy to predict product. This is called a peroxyacid. A peroxyacid is a carboxylic acid. See, if I take away this oxygen, you can recognize this functional group as a carboxylic acid. But there's this extra oxygen in there. So this is actually like a peroxide, just like hydrogen peroxide has an extra oxygen in it, and we call it a peroxyacid. Now this is just acetic acid that is the peroxyacid of acetic acid. You can have a peroxyacid of a lot of carboxylic acids, like benzoyl peroxide is a peroxyacid of benzoic acid. And there are several other different peroxyacids. How is it you recognize them? You recognize them by the carbon-oxygen double bond and then 1, 2 oxygens in a row bound to each other. These are pretty high energy. And when you mix them with alkenes, the double bond reacts with the peroxyacid. It takes this oxygen and puts it on top of the double bond so that the double bond here is gone, and you make a 3-membered ring with the oxygen in it. This structure is called an epoxide. The name of this one is 2,3-epoxybutane. The other product that is made, since you're taking an oxygen out of the acetic acid, the peroxyacid over here, you make the carbon. Okay, here is an example of an epoxidation. We're starting with cycloheptene, and the peroxy acid that we're using here is something called metachloroperoxybenzoic acid, or otherwise abbreviated MCPBA. How do you recognize a peroxy acid? The way that you recognize a peroxy acid is you look right here and you see 2 oxygens bound side by side to each other. Whenever you have 2 oxygens bound side by side, except for in oxygen, but in any covalent molecule besides oxygen, where you have 2 oxygens bound to each other, they're peroxides. And this is what's called a peroxy acid. They're high energy, and the oxygen is so labile that it is going to easily make other high energy compounds. So what happens here is the peroxy acid donates that one oxygen over here to the 3-ring compound, and it gives you an epoxide over here. Notice that the product of this acid is a very stable compound, a carboxylic acid. See how the peroxy acid changed to a stable carboxylic acid and made a high energy but lower energy compound. Is still high energy, but it's much lower than this peroxy acid. Okay, the mechanism is one step. This is a really neat mechanism. If you look at this double bond reaches out and grabs that oxygen and puts a bond here. This hydrogen to oxygen bond reaches out and puts a bond here. And because it's got this oxygen over here, it can do this really neat cyclic reaction where the electrons move over here and these electrons move over here. And of course, these electrons move over there. And the product is now this ends up being the carboxylic acid. And then this part ends up being the epoxide. So go ahead and look at this compound and this one and write down the structure of the epoxide that forms when you react it with peroxyacetic acid. Okay, this compound actually adds an oxygen on top. This is fewer carbons on this side, so what we find is it adds to this side of the double bond because there's less steric hindrance there. And this is the product that we get, an oxygen bound to 2 carbons that used to be in the double bond. If I look at this molecule, what do I see as a result? I get an oxygen bound to each of these carbons. Remember, the easiest way to predict outcomes is to take the reagent that's given to you, redraw it, then erase things and modify it to fit the change that the reagent does to it. So I just redrew this over here, erase this double bond, and then put a bond and a bond to oxygen in a three-membered ring. If I look at this, that's exactly the same thing that I did. I took this compound and redrew it over here. I erased the double bond, and then I drew the epoxide in to the carbons that used to be in that double bond. So what kind of compound results when these alkenes are treated with hydrogen gas and a palladium compound? Well, go ahead and figure out the answer and then restart the lecture when you're through. Okay, this compound here, you would, with hydrogen gas and a palladium compound, all that would happen is you would add a hydrogen here and a hydrogen here, and that would disappear. The double bond would disappear. And so we would get this bicyclic compound. If I look at this compound, what would happen? We would get this compound. Notice you add a hydrogen here, so there's two here, and you add a hydrogen here. So what compound results when these alkenes are treated with deuterium gas and a palladium compound? Pause it, figure it out, and then restart. The product that results from this would be the same as hydrogenation, except you're putting on deuterium instead. So this would end up putting a deuterium here and a deuterium